Okay, so we are talking about pumping lemma, application of pumping lemma. So, we just have this is a powerful technique to prove a language is non-regular. So, using this technique we have seen language like this 0 to the power n, 1 to the power n is not regular, is not regular. Okay. So, it is a using, we have seen this using pumping lemma. Pumping lemma is the necessary condition for a regular language. If a language is regular, then there will be a n. N is basically the number of language regular means we have a DFA which is accepting the language. So, n is the number of state in the DFA. So, then we have that n, and if we take any string which is greater than n, then which can be written as uv, where uv will be length is less than n, and then this u v to the power I w will belongs to L. This is the necessary condition where I is greater than or equal to 0. If I is 0, then u w, then we can pump there. Okay. So, it is u 0, with u we go some state, then from there with v we go here, and then with w we can go to the final state. So, since it is a loop, we can keep on pumping there, that is why it is called pumping lemma. So, using this pumping lemma, we have seen few language which are not regular, which is not satisfying the pumping lemma, and it is a necessary condition. Okay. So, with help of that we will show a few more language which is not regular. For example, we take this language a to the power n, b to the power m. N is greater than or equal to m. We show this language is not regular, so sigma is on a b. Okay. So, this means what? This is the number of b's. Number of b's are more number of b's than a, okay, because n is more. So, more number of a's than b's. Anyway, so if we take the reverse of this L of r, which will be basically this will come here a to the power n, sorry, a to the power n. This is just the reverse. So, n is greater than this. Okay. Now, if we have seen if a language is regular, the reversal is also irregular. Then, so if L is regular, then L prime also. This we have seen. This is the property of a regular set. Okay. Now, in this is say L1. So, here we just exchange this A B. So, we just exchange this A B, interchanging A and B. That means, A is going to B, B is going to A, this mapping, and this is a homomorphism. We have seen the homomorphism, this is a homomorphism. So, if you do that, then we get L prime, which is basically a to the power m, b to the power n. We are exchanging a by b, b by. So, a is going to b, a particular string, and b is going to a particular string. So, this is a under this mapping, sigma is going to sigma star, where h of a is a b, h of b is a. So, this is a homomorphism, which is a substitution, and we know the regular set is closed under substitution. So, here n is greater than equal to m. Okay. So, if you look at this, now if this is regular, then L prime will be also regular. We are assuming this is regular. We are assuming this is regular. Assuming L is regular. That means L prime is also regular by that assumption. This is also regular. Now, we know the regular set is closed under substitution or in particular homomorphism. So, that means this is regular. So, L and L prime are regular. Now, if you take the intersection, then what it will be? L and L prime. If you take the intersection L intersection L prime, this will nothing but a to the power n b to the power n greater than or equal to 0. Now, since L is regular, L prime is also regular. So, their intersection is also regular. That is another properties of regular set. So, this has to be regular, but we know this is not regular. We have proved this using pumping lemma. So, that means what? There is a contradiction. Since this is not regular, so this cannot be regular, then this cannot be regular, then this cannot be regular. So, this implies contradiction, that means this is not regular. Okay. So, this is one example. Even we can directly using pumping lemma to show this is not regular. So, this proof will be, this direct proof will be there in the lecture note. Okay. So, this is one direct application of the pumping lemma. Now, we will prove a theorem which is coming from the pumping lemma on a regular set. Okay. So, this theorem is telling, so suppose the set of string accepted by a finite automata M with n states. So, that means this set is regular. If we have a regular set, then we have these properties is either it is empty, or if it is non-empty, then non-empty if and only if the finite automata M is accepting a string of length less than n. Accepting a string of length less than n. If it is accepting a string of n less than n, then say L is that set of all string, which is a regular set. That means we should have a automata to accept that. So, that automata is M. Now, this set we want to check whether this set is empty or not. If it is non-empty, means we should have a string which is accepting this string which is accepting by this automata and whose length is less than n. Okay. And when it will be infinite, it is infinite if and only if M accepts some string of length L, where L is belongs to n less than equal to 2n. Okay. It will be infinite if we have a string of length more than n, then it will be an infinite length. This is a theorem. This can be proved using pumping lemma. So, first part is what? First part is, if it is non-empty means if and only if. If it is non-empty, that means we have a string which is accepting it, and if we have a string which is accepting it, then it is a non-empty. And the second part is coming from the directly coming from the pumping lemma. That means, if we have a string of, so this is consist of n state. Now, if we have a string of length L, so then we can write this W, Z is U V W, where U and V are less than n length, then we can pump in V. So, then U V to the power I W will also belongs to L. So, this will give us the infiniteness using pumping lemma. So, it will be either empty or finite or infinite. So, when it will be empty, if there is no string of length less than n, and when it is finite, if we have a length of string less than n, and when it is infinite, if we have at least one string of length more than n, then it is this. Okay, so, we will use this theorem to see whether two DFA is equivalent. So, this theorem we will use. So, the details proof of this theorem will be given in the lecture note. Okay, so, we will use this theorem to see whether two DFAs are equivalent. So, two DFA, finite automata. So, that means we want to see given two DFA, say M1 and M2, whether they are equivalent or not. So, what do we mean by they are equivalent? Equivalence means if they are accepting the same language, that means if L of M1 is L of M2, which is then we say these two DFA are equivalent, then M1 M2 are equivalence. Okay, so yeah, so how to show this? We have to check whether two DFAs are equivalent or not. So, how to check this? So, to check this, suppose M1 is corresponding to L1, which is nothing but L of M1, and M2 is corresponding to the language L2. Okay. Now, we want to see whether this L1, L2 are same or not. So, for this what we do? So, since they are coming from the, so these two are regular. So, now we construct this set L1 intersection L2 complement union of L1 complement intersection L2. Okay. Now, this we denoted by L. Now, what is L? Is L is regular? Is L is regular? Yes, L is regular. Why? Because L1 is regular, L2 is regular. So, L2 complement, L2 is regular, L2 complement is regular. Then we have, this is the closure properties of the regular set. Now, we know intersection of two regular set is regular. So, this is regular, this is regular. We know the union of also regular. So, this is L is regular. So, once L is regular, that means we have a DFA M3 which is accepting this. Okay. Now, if this is, now we have to check whether this is empty or not. If this set is not empty, then these two DFA are not equivalent. So, if M3 accept a string, if and only if L2 not equal to L1. So, that is the way we can check whether this is a regular set. Now, we have to check whether this regular set is empty or finite or infinite. So, that we can do using some algorithm to decide whether set regular set is empty or not, empty, finite, infinite. So, if it is not empty, if there is a string which is belongs to this, because if x is belongs to this L, that means L1 L2 cannot be same. If they are same, this has to be empty, because the way we have constructed this. So, now we will talk about how we can check whether a regular set is empty or not, empty, finite, infinite. So, this we can use the pumping lemma to check this. So, this is the algorithm, algo to decide whether a regular set is empty, finite or infinite. Okay. So, this is we have just now we have seen the theorem. So, since this is a regular set, so we have a automata which is accepting. So, the set of string accepted by this by a finite automata M with n state. So, this just now we have seen is non-empty if we have a if and only if we have a language, we have a string of length less than n, and it will be infinite if we have a string of more than n. So, this way we can prove that using the pumping lemma. But there are other ways also we can see this, because once we have a finite automata, then we can see whether this. So, this is a better algorithm, algo to check the emptiness. Okay, so, we have given the automata, given the finite automata n. So, finite automata means we have some, this is a graph. We have a graph, we have a starting state, then we have some state from the starting state, say q1, q2, q3, something like that, and we have some state from here, something like that, and then we have some final state qf1 like this, and we have some transition on this. So, this is basically a graph. We have a graph. Now, in this graph what we can do? We can do the graph's traversal. We know there are two ways we can do the graph traversal. What are two ways? One is BFS, the breadth first search, which search the graph level wise. This is the level 0, this is the next level like this. So, we reach to the all the nodes level wise, level 0, level 1 like this. From the level 1 we reach to the all the nodes which are connected with the level 0, which are connected to the previous level node. So, leveling, this is the one way we can do the search, that is called BFS. Another way is DFS. DFS is nothing but depth first search. So, we start with a vertex and we keep on going until we stuck. Once we stuck, we come back to that position and we explore the new path like this. So, what we do? We do the graph search. Okay. We do the graph search and we found from Q0 where we can reach, all the possible nodes we can found where we can reach. And in that reachable nodes, reachable states or the nodes, we can say graph sense it is nodes. The reachable states where from Q0 we can reach, we can list it out, and that will take in the both the algorithm will take the time complexity order of n square. With the time order of n square we can find that. Okay. Now, so we have the list from Q0 where else we can go from Q0 by using the graph search, and then from there what we can do? We can just check whether any of this reachable node is a final state or not. Okay. So, that if there is any final state, then it is non-empty. If there is no final state, then it is empty. So, let us just write this. Okay. So, this is graph reachability. Okay. So, so what we do? We construct a set of states or nodes, set of reachable states from Q0. So, this we can do using the graph traversal or this BFAs or DFAs, and that can be done if there are n state in the automata, that can be done order of n square the time complexity. Okay. So, we construct this set. Now, if this set contained an accepting state, if this set contains an accepting states, then it is non-empty. We check that, and if the output is no, if there is no accepting state, then the language is L is empty. Otherwise, if it is accepting, it is containing any accepting state, yes, then it is non-empty. And L is non-empty means that that DFAs are not equivalent. The way we constructed the DFA, they are not equivalent. Okay. So, even we can do it by using the regular expression. So, so how we can do it? Using the regular expression to check whether the graph is non-empty. So, we know L is regular, because the way we have constructed. Okay. Now L is basically what? L is L1 intersection L2 complement union of L1 complement intersection L2. Now, we know this how to construct a DFA for this, because this is a we know the for intersection we can construct a DFA, for complement also we can construct a DFA, we can reverse the states, I mean the accepting state, who are the non accepting state, we can make it accepted, make it the new accepting state. So, that will give us the complement. Intersection also we have seen, union also we have seen. So, basically we can construct a finite automata for this, and then just now we have seen that by using the graph search we can check that, but there is another way to do that using the regular expression. So, this L L we can have a regular expression for this R say. Okay. Now, we check whether L of R is basically L, empty or not. So, this we can check using the number of operator on this regular expression. So, regular expression R is either 3 of this way, R will be R 1 plus R 2. So, in that case L of R is nothing but L of R 1 union L of R 2. Now, it will be empty if both are empty. If the regular expression R 1 and R 2 both will corresponding to the empty set. This is one possibility. Another possibility is it is concatenation R 1 R 2. So, L of R is basically L of R 1 L of R 2. So, that means what? That means if empty means either one of this empty, then it will be empty. Okay. No, both has to be empty, because if one is empty then epsilon will come. So, both has to be empty. So, that way you can check by the this inductive method. So, we are reducing the number of operator. And now, this last one, if R is all star, that means L of R is basically sorry R 1 star. So, we can check whether L of R 1 is empty or not. If L of R 1 is empty, then this is empty set. So, this way also we can verify a set is a regular set is empty or not. Thank you very much.